The learning objectives of this chapter are to know who can test the atmosphere in an enclosed or confined space, to know when the atmosphere in an enclosed or confined space must be tested, to understand the different methods that must be employed in testing the atmosphere in an enclosed or confined space, and to understand the functions of different meters and other test equipment, together with their limitations. We have already acknowledged the potential hazards presented by the atmosphere within an enclosed or confined space. It is therefore relevant that we should now examine test equipment, test procedures, and required readings in more detail. The readings quoted in this section for safe, unprotected entry into a space are generic minimum readings taken from standard industry regulations and guidelines. If the vessel operates to a safety management system which requires higher or more specific standards, then these should be observed and followed. There are many models of atmosphere test meters available, although most companies try to standardize across their fleets in order to make supply of parts more streamlined and training on the equipment easier. Click on the labels for more information. Oxygen analyzers test only for oxygen content levels. That is, they assess and display the percentage of oxygen in a sample drawn from a tank or compartment. Readings are expressed as percentage by volume. A reading of 21% oxygen by volume on an oxygen content monitor must be obtained before unprotected entry is permitted. This means entry without an externally generated air source or self-contained breathing apparatus being used. A combustible gas indicator, or explosimeter, is an instrument for detecting a combustible gas-air mixture, usually measuring its concentration in terms of the lower flammable limit, or LFL. A combustible gas indicator cannot be used to detect oxygen deficiency, nor is it suitable for indicating levels of toxic gas at or around the applicable occupational exposure limit, where there is solely a toxic rather than flammable risk. This level will be much lower than the flammable limit, and the indicator will probably not be sufficiently sensitive to give accurate readings. Many explosimeters will also not detect the presence of a flammable vapor in a space filled with inert gas, although some models do have an additional attachment that allows the meter to be used under such conditions. In such meters, a controlled air supply is also fed into the analyzer unit, and the observed readings have to be entered on a graph or table to obtain a true flammable vapor reading. An instrument capable of providing accurate reading at low concentrations should be used to judge whether an atmosphere is safe for entry. Combustible gas detectors are calibrated on a standard gas. When testing for other similar gases and vapors, reference should be made to the calibration curve supplied with the instrument. Note that the range of gases that can be tested for with this equipment is limited. Particular care is required should accumulations of hydrogen be suspected. In deciding whether the atmosphere is safe to work in, a nil reading on a suitably sensitive combustible gas indicator is preferable. But where the readings have been steady for some time, a reading of less than 1% of the lower flammable limit is considered acceptable. Some meters, specially designed for enclosed space entry on ships, combine oxygen and combustible gas measurement in the same unit, sometimes also with additional specified gas sensors, such as for carbon monoxide and hydrogen sulfide assessment, also incorporated. While this makes atmosphere analysis easier, care should be taken not to confuse the respective readings. Advances in technology have reduced the size and increased the capabilities of monitors in recent years. Many companies require under their safety management system that personnel involved in entry into enclosed or confined space carry personal monitors, which continuously assess the atmosphere in the vicinity of the wearer. However, such monitoring equipment is designed for personal use purely to provide a warning against oxygen deficiency and hydrocarbon concentrations when there is a change in conditions in the immediate vicinity of the wearer. In other words, they warn the user that something hazardous is happening close by, and are not representative of the overall atmospheric condition of the space. These monitors should not be used as a means of determining whether a dangerous space is safe to enter in the first place. They should be used only in support of the initial remote readings, and not as an alternative to or substitute for such tests. Low-level traces of toxic gases are tested for using specialized detection equipment. Chemical tankers normally use portable equipment because of the number of compartments and range of products they carry. Other types of vessel, where the toxic gases are more consistent, may have a fixed system with standard sensors. Portable equipment commonly consists of a pump, which draws an air sample through a glass detection tube containing a reagent that colors when exposed to a particular gas, if it is present in the sample. The value is then indicated against a graduated scale on the tube. Typically, this will be tens or hundreds of parts per million, in other words, at a very low level. This specialized equipment is necessary because most standard electronic meters cannot test for the range of single products, read accurately to such low levels, or display the readings in such small increments. The readings obtained by toxic gas detection equipment should be compared to the occupational exposure limits for the contaminant given in the appropriate international industry safety guidelines. These occupational exposure limits provide guidance for the level of exposure to toxic substances, which should not be exceeded if the health of persons is to be protected. Note that the range of tubes available does not cover every gas, nor can a single tube normally detect multiple gases. The test procedures are different for each tube, and the operator should always consult the manufacturer's instructions before use. Chemical tankers must carry valid gas detection tubes for the cargoes on board and to be loaded. When a toxic chemical is encountered for which there is no tube manufactured or any alternative means of testing available, then the additional requirements should be followed. That is, the use of breathing apparatus and other personal protective equipment. Testing of the atmosphere in an enclosed or confined space for the purposes of authorizing entry should only be carried out by persons trained in the use of the equipment and listed as approved operators under the safety management system. Testing should be carried out before entry and at regular and frequent intervals thereafter, whilst entry continues. Some monitors have a data logging facility, but in any event, records of periodic tests of the atmosphere in an enclosed or confined space should be made. Such records are filed after use, along with the enclosed space entry permit, for examination by auditors and inspectors. If possible, the testing of the atmosphere before entry should be done by remote means. This may be with a fixed probe in a hold or void space, or with an extension line on a portable monitor. This is the safe way to test, in that it does not expose anyone to the additional hazards presented by entering the space. Vessels where entry into enclosed spaces is routine or anticipated are usually fitted with or supplied with the appropriate equipment. In some vessels, however, entry into an enclosed or confined space may be an exceptional and unanticipated event, and they may not carry equipment with remote measuring capability. In this situation, an initial protected entry must take place to carry out measurement within the space, irrespective of the suspected condition of the atmosphere. The person selected to enter the space to test the atmosphere must wear breathing apparatus and rescue harness, and must position himself only where he can be hauled out in an emergency. On some vessels, it may be that certain spaces are only accessible by passing through another enclosed or confined space, as for example a double-bottomed tank accessed through a manhole in the bottom of a side ballast tank. In such cases, this must be carefully planned and all precautions accounted for. It may be that the operation becomes a two-phase entry, with separate atmosphere test readings and an intermediate station for a second watchman. If the enclosed space is a cargo tank or hold, it is assumed that cleaning operations are completed and the space has been cleaned to the maximum possible extent, followed by adequate ventilation. The meter used to test the atmosphere should have been purged and zero set immediately before use and allowed to stabilize. Oxygen meters should be zero set in clean fresh air, not immediately adjacent to the hatch or vent risers, where they may be subject to fumes being expelled from the tank. The ventilation should be stopped about 10 minutes before any tests are made, and not restarted until the tests are complete. This is to allow the atmosphere to settle into an even representative condition. For readings subsequently taken while the space is occupied, ventilation should not be stopped, but run continuously. Where possible, testing must be carried out at different levels and in different sections of the space, thus increasing the possibility of detecting any pockets of oxygen-deficient atmosphere remaining in the space. Suspected vapours, which have a relative density greater than that of air, will be found at the bottom of the space. Vapours will also tend to remain where the ventilating airflow is least effective, that is, at greatest distance from the inlet, and particularly between frames and stiffeners. Note that an extension fitted to a portable monitor may require additional steps in the test procedure. Most models today are electronic, but where an air sample is drawn up to an analyzer unit on deck, a longer sampling time may be required to allow fresh air to be purged out of the piping and ensure that an accurate reading is obtained. Note too that some models are not capable of drawing a sample above a certain height and cannot therefore be used to test the atmosphere in the bottom of a tank from deck. When it is required to gas-free a cargo tank on an oil tanker after washing, it should first be purged down with inert gas to reduce the hydrocarbon content to 2% or less by volume, so that during subsequent gas freeing, no part of the tank atmosphere is brought within the flammable range. This additional gas freeing is also needed to remove toxic products introduced with the inert gas. Direct measurement of trace components of inert gas is not required when that subsequent gas freeing reduces the hydrocarbon concentration to 1% of lower flammable limit or less, in conjunction with a steady oxygen reading of at least 20% by volume, because this is sufficient to dilute these components to a safe concentration. The critical importance of atmosphere testing equipment is obvious, and it is essential that such equipment is always maintained in perfect working order. It should be properly stored, regularly tested, and calibrated in accordance with the company maintenance schedule and manufacturer's guidelines, and always cleaned and checked after use. Detailed records should be kept of all testing and maintenance. On the 4th of September 2001, The chemical tanker Rhinestone was anchored off Rotterdam awaiting cargo orders. Even though there were no instructions, the master decided to prepare the tanks anyway. The previous cargo had been naphtha. Because of the vapor density of the product, the plan was to ventilate the tanks and then eject the cargo residues, collecting them in a slop tank. No water cleaning was planned. Ventilation was achieved by a flexible large-bore trunking connected to the deck ventilation line and inserted through an adjacent tank cleaning hatch. The trunking was only pushed inside the top of the tank and not lowered down to the bottom. The tank lid was kept only cracked open in order to create a slight back pressure in the space. In order to eject the tanks, the normal procedure was for a man to enter the tank and put the ejector pump suction hose into the sump, directly under the foot of the deep well cargo pump. The first tank to be ejected was number 8 starboard, and the chief officer tested the atmosphere at around 10:30 hours, recording 15 to 25% LEL and 20% oxygen content. The chief officer had given instructions that self-contained breathing apparatus was to be used in the tank entry, but he later observed a number of the crew exiting tank number 8 starboard after ejecting wearing filter masks. The chief officer spoke to one of the men who stated that they preferred to use the filter masks because the SCBA sets were heavy and awkward to use. Work continued through the day, and the chief officer later left the deck to get some rest. At around 16:35 hours, the crew turned their attention to tank number 6 port. The tank was not tested before entry, the assumption being made that conditions would be the same as in number 8 starboard. The deck cadet had by now arrived on deck and was assigned as watchman. 3 crewmen went into the tank, 1 to place and tend the suction hose, and 2 to squeegee or sweep any remaining product towards the sump. At around 16:45 hours, the deck cadet saw one of the men down the tank collapse. He immediately informed the second officer on the bridge, and the general alarm was sounded. The master quickly appeared on the bridge, but discovering the situation, he went down onto deck straight away. On the way, he met the third officer and instructed him to collect a rescue line and harness from the after-deck store. Meanwhile, one of the 2 crew members still standing in tank number 6 port left the tank to get a breathing apparatus, while the other crew member stayed with the man who had collapsed. As the man arrived on deck, the deck cadet took the filter mask from him, put it on, and entered the tank himself to take a breathing apparatus set down. Once he had handed it over, he returned to the deck. The man who had stayed inside fitted the mask to the casualty and opened the air supply valve, establishing at the same time that he was breathing. The crewman who had left the tank now returned wearing a self-contained breathing apparatus and took over from his shipmate, who had been wearing only a filter mask throughout the incident. As he exited the tank, the master took the filter mask from him, put it on, and entered the tank. He tried to move the collapsed man, but he found him too heavy, gave up the attempt, and climbed back out onto deck. By this time, both equipment and men had started to arrive on scene, including the harness, line, and a resuscitator. 2 more men donned self-contained breathing apparatus and went down inside the tank. The harness was lowered and fitted to the casualty, who was then hauled out onto deck. During this recovery operation, the master collapsed on deck. The second officer contacted the Netherlands Coast Guard from the bridge and requested medical assistance. After some discussion, it was agreed that the Rhinestone should heave anchor and proceed towards the entrance to the port, in order to minimize further delays, and a helicopter would be mobilized. In the meantime, repeated and prolonged attempts were made to revive the master, and care was administered to the man who had been brought out of the tank. At 18:30 hours, the helicopter arrived bringing a doctor. The master was pronounced dead at the scene. The man who had collapsed in the tank spent the night in hospital ashore, but returned to the vessel the following day.